Physics 2212 lines of charge. In this lab, an analysis was done using the data from Lab 1, but instead considering the tape as a uniformly distributed charge instead of a point charge. The purpose is to observe clear tape interactions, predict the charge of the tapes, determine the excess charge on the piece of charged tape, and simulate the interactions between two charged pieces of tape with the Python program. A preview of the results is shown below. The charged clear tape has a net positive value charge, and the charge of the tape is 1.99 E negative 8 coulombs. The tape is deficient of 1.235 E11 electrons. One of the fundamental principles used is Newton's second law, which states change in momentum over change in time equals a net force on an object. Gravitational force near the Earth's surface is F equals mg, with the gravitational constant being 9.m per second squared. The next fundamental principle used is the electric field for a rod with a uniformly distributed charge. The electric field considers the separation between the observation point and the length of the tape. We use the following equation as an estimator for the charge on the tape. The last fundamental principle is electric force Coulomb's law. This states the strength of the electrostatic force that attracts or repels 2 point charges is inversely proportional to their distance from one another and directly relates to the product of their respective charge magnitudes. It is also equal to the product of the charge at the observation point and the net electric field. As we discussed in the introduction, the physics ideas are Newton's second law, electric field of a rod with uniformly distributed charge, and electric force. Below are more figures that relate to these ideas. The assumptions made are that the charge is evenly distributed along the tape, so we can model the U-tapes as multiple singular point charges in the code. The procedure for creating charge is the same for both tapes, so both tapes have the same amount of charge, and finally air resistance is ignored. The reasoning for the models is that we can model the U-tapes as multiple singular point charges in the code because we assume the charge is evenly distributed along the tape. The system is the suspended U-tape, the surroundings is the held U-tape and earth, and at equilibrium the net force on the suspended U-tape is 0. Here are the procedures used in the lab. Here are the observations observed from Lab 1. Some important points are that the pen had a negative charge due to its interaction on the clothing. The electrons transferred onto the pen from the clothing, and since the U-tape was attracted to the pen with a negative charge, this shows the U-tape had a positive charge, and this is because opposites attract. The separation distance 0.025 is equivalent to the magnitude of vector r. Here are the calculations and data from Lab 1. We can use the equation for the electric field of uniformly charged rod to estimate the charge of the tapes. We treat the top tape as the observation point and the bottom tape as a charged rod. We would set the magnitude of the gravitational force on the tape equal to the magnitude of the electric force reaction as shown below, and Q equals 1.99 E negative 8 coulombs. We can use this value of Q to approximate the charge of the tapes. Here are the constants used in the code. Then here is the portion about the electric field and creating the tapes. Here is the portion where we calculated the net electric force. Finally, here is a computational model generated using our code. Looking at the data and model predictions, they look pretty similar, and the value of deficient electrons was 1.235 E11. The explanation for the errors are shown below. The separation distance could have been inaccurately measured. The tape length and width could have been inaccurately measured as well. The suspended U-tape could have not been parallel to the other U-tape, and this would lead to the inaccurate separation distance discussed in the first bullet point. And then there was also error in calculations due to rounding. The answer to the what-if question is the line charge model has a greater charge. The line charge gives a more accurate approximation of what the actual charge would be because it is a better representation of how the charges would be distributed on the tape. The answer to the why question is that the differences are caused by the fact that charge is dispersed more equally over a rod-like structure rather than a single point charge. The line charge model takes into account both the rod's length and its distance from the observation site. The line charge value is closer to the real value because it models the charge distribution on the tape more realistically than the point charge model.